Well, it's not. It's probably not going to be like the full Appendix D. It'll just be the data that you'll need from Appendix D.
And you decide what calculators can I use on the test?
Yeah, go ahead and use that one on the test.
And then, you know how we can put the 9 to 10 alpha centers on Wednesday? Would it be possible to do it tonight instead?
Yeah, that's possible. I could do it tonight.
Thank you. I was looking at the past exams,
Mm-hmm.
and number 16 on the last one, is CaCO3 solid and CaO solid plus CO2 gas with a P of 0.25 bar. What temperature to make it spontaneous?
Mm-hmm.
I wasn't sure how to do it. Or how you would set that up.
How would you how would you change delta G? Are there any ways you can change delta G? All right, you could try temperature. Are there any other ways? Does pressure change delta G? Is it possible to change the pressure and change delta G? You have to go back and think of all the ways that you could change delta G, because delta G dictates whether a reaction is spontaneous or non-spontaneous. If delta G is positive, then it's non-spontaneous. So it might not be possible, because what you have to do is, if it's positive, you have to make it go to 0 and then to negative. And so you would have to see, is it possible to get delta G to go to 0 for one, and then see if it's possible to get it to negative for another. And so all the strategies, the general strategy is, what are the ways to make or to change delta G? All the ways. Can you list all the ways? Because you'll need to know all the ways to change delta G. So you can try temperature and then see. Maybe temperature will do it. You can try that. And then the question is, will pressure do it? You have to, do some research and look. Is it possible to change the pressure? To see. Is there an equation that shows it with maybe pressure? Mm-hmm. You can find any pressure equation. Did anybody else find any pressure equation? Mm-hmm. That one you could use too. That's a possibility, but it depends on the reaction you're looking at, whether that one will work or not. But you could leave it in the form of K. That shows the Clausius-Clapeyron style equation like that will show how K changes with temperature. K changes with temperature because K is a function of temperature. So you can see if you could swing K from the reactant favored to the product favored side. That's one of the options you could do. But when you're looking at spontaneous versus non-spontaneous, you're looking at delta G, so you got to figure out what are all the things that change delta G. And so you should take a look and see the equations, and then see if you can find an equation. What problem was that? Oh, this is asking you to change the temperature. So you just figure out the temperature at which the delta G goes to 0. This is the problem with thermodynamics is thermodynamics, you have to figure out, this is what you have to do. Make a list of all the equations and then make a little footnote or a little annotation or a little note when you can use that equation, and what you can do with that equation. So what you should do is you should list all the equations that you have and then see if any of those equations would fit. Mhm. Yeah, pressure 0.25 bar. So you'd look, is that under standard conditions or non-standard conditions? Then that eliminates most of the equations. You have very few equations to choose from now because you've just eliminated practically all of them. From those very few equations, you would look which one would work in this appropriate situation because you don't have to necessarily derive them. There are some equations that you should know. I mean, I'd write the basic equations for you, but some of them you have to put it together, you know. But what you do is, okay, then that leaves very few equations. So in this, the primary goal was maybe thermodynamics is a tough subject. So the main thing you want to focus on is to be able to use the equations and then use them in the appropriate circumstances. That is, you don't want to use the wrong equation for the wrong circumstance because that's a very common error. And so at this point, I wouldn't worry too much about wouldn't worry too much about you know conceptually. Just understand the equations. That's the first step. Just understand the equations and when to use those. And so when you boil it down, you'll only have one equation that you can use for this particular one, and it's one of the equations I wrote on the board. So take a look. It's going to have variable temperature and variable non-standard conditions. There's only one equation. Yeah, only one equation that you can use. Try to find it. If not, you ask me tonight. We still can't find it. Actually, make that two because if you do what Colin says, you could use two equations. You can use depends on how you want to do it, but essentially the same equation, just different um, variations of the same equation. Well, I was hoping not to post the answer key because I think it's more beneficial if you could figure it out yourself. I mean, it's open book. So if it's open book, you should be able to figure it out yourself and then have some confidence that you have the correct answer since you can just look it up, the whatever's needed. But I may just post the answer key for this. I do have the answer key. But I think, since it is open book, then you know that you're prepared if you can answer the questions and be confident in your answers. That is, you don't have to ask for what the correct answer is, because um, that's that's the way you want to. You want to have enough confidence in your answer that you know it's right, you know, and that would be the best. But if you're always uncertain, did I do this correct or not? Barring some algebraic mistake or something, then, especially with the equations in this chapter. But I think a lot of people probably didn't quite get as far. So I'll probably post the people that, you know, interest. But yeah, that's critical though. The critical step is, because if you see other variations of the problems, then you want to know all the equations. It doesn't mean you have to memorize them all, but you should know, non-standard. You have a system standard 298, standard not 298. You know, and just see. Then you look at the conditions you're given. Not standard, not 298. Then see what you can do with that. But try that out and see if you can figure it out. I think that would be helpful. But were there other questions too? Mm-hmm. In-person office hour after it was time is it 4:20 to 4:50 is the official time in person. Yeah, this particular problem, I gave the data on the board. So I just wrote up the delta H of formations and the S. And so you didn't have to have any of those memorized. So you can do that. I also wrote up equations on the board too. So this is the basic equations. Yeah, right. So multiple choice. I'm going to put more multiple choice probably on yours. Or maybe something similar to this. It could be similar to this, 2 points. Some calculations. Other questions? Yeah, the asterisks mean just read it. You don't have to do the problem. Just I'll show you. Although 94 was it? 96. 500 Kelvin, 10-liter equilibrium mixture contains. Mixture is quickly chilled. Oh, that's right. Chapter 13. Yeah, this is just read it. I made the assumption, and this includes the last problem on the practice test. We make the assumption of what? In general, if we're working under non-standard conditions, that's one thing. But if we're working under standard conditions, we make an assumption of what when we change the temperature. We assume that the yeah, delta H and delta S don't change much, but they do with temperature. And so this is just showing something about that, This is making another assumption that the heat capacity doesn't change, but it does. And so the equation is actually a bit more complicated. 96. In fact, if you want to see the variation with heat capacity, there was a problem in Chem 1A. Forgot which chapter it was. So there's a problem that showed the heat capacity with temperature, or specific heat with temperature. There might have been specific heat. Well, it was like a third order equation or more. And it was a problem. It was a problem regarding something not specifically related to calculating heat capacity. It's just showing the equation to use if you wanted to determine the heat capacity at different temperatures. Maybe this was it. Yeah. This also shows it. In Chem 1A, there was an equation that looked very similar to this, except it was a little higher order. This one, the molar heat capacity at constant pressure is equal to 97.78 plus this. Here's the temperature. It's being factored in. This is an empirical equation. So the equation gets more complex if you add that in as well. Number 96. Yeah. Just read the problem. It's not. Nicole, did you have a question on the homework also? Yeah. That the problem on the left is just making sure you use the correct equation. One of the things though conceptually is why would you use, if that's under non-standard conditions, why are you using delta H under standard conditions and delta S under standard conditions to solve that particular problem? This is going back to number 16. When you look at the equation could have delta H and delta S under standard conditions. And so the question comes up conceptually, why are you doing that? It's under non-standard conditions. Does somebody have the answer to that? Right. When you go back to the original delta G under non-standard conditions, delta G under non-standard conditions is equal to delta G naught under standard conditions. So why is it equal to delta G naught under standard conditions? Well, because we add the factor plus RT ln of Q. The RT ln of Q is a correction term. And so we reference the standard conditions and then correct it for non-standard conditions. So that's why those appear in the equation for non-standard conditions. So what you want to do is when you write out these equations, you want to write these little notes for you so that you can better understand the application for the particular equations. 41? Yeah. In the synthesis of gaseous methanol from carbon monoxide gas and hydrogen gas, the following equilibrium concentrations were determined. Calculate the equilibrium constant and delta G naught R. So in this particular problem, You what you want to do here, let me just, is first figure out the delta G expression. The delta G expression is going to be the products of the reactants. I mean, not the delta G. Which one are we doing? This one. Here, calculate the equilibrium constant delta G naught for the reaction. Okay, so this one, is it under standard conditions or non-standard conditions? Non-standard. But there are different approaches we can do. And so this is why, like in thermal, there are a lot of different variations that we could do here. Well, one thing is they're telling us the equilibrium concentration. So if they're telling us the equilibrium concentrations, what we can do is we can just calculate equilibrium constant, K. And so I know it's they're asking us for the equilibrium constant first. So let's do that one first. And here we just say that the equilibrium constant expression, K, I guess it's not working. Did you calculate K for this? You got a different answer than what they got? Oh, what did you get for your K value? What did they get for their K value? All right, so K, the situation here is this. When we're calculating the K, we have three different choices of K. What are the three different choices for K that we have? Yeah, we just have K equilibrium, which is the thermodynamic. This K is going to be based on all the delta G's equation. But this K, it could be KC, it could be KP, or it could just be KEQ. I mean, we only have the. Now, when you compared your answer, did you calculate the KC or the KP, or which one did you calculate, and which one did the book list as the answer? Because what they're saying here is they're just saying calculate K, the equilibrium constant. If they're saying calculate the equilibrium constant and then delta G, then I'm assuming they're talking about KEQ. They must be talking about KEQ because this is all gases. If it's all gases, then we should be calculating KP or KC. KP, but they're giving us all molarities. They're giving us all molarities to throw us off, basically, because we're going to calculate KC, but they're being vague about this, and they're saying calculate K. Well, we got to assume they're talking about KQ because they aren't specifying KC or KP, and KEQ is going to be the most general one. And so, in this case, sometimes it doesn't make a difference, but in this case, it makes a difference. Is KC and KP, are they going to be the same? No, because delta N of the gas, when we look at delta N of the gas, we're going from 3 moles of gas to 1 mole of gas. Delta N of gas is -2, we're losing 2 moles of gas. So they aren't the same number. And so the situation here is they're asking us for delta G right after calculating equilibrium, which means it's got to be KEQ that they're asking for. So we're going to calculate KEQ. and then do that. Now, there are two ways we can do KEQ. One is we can calculate the pressures, but we don't have the volume to calculate the pressures. But even if we don't have the volume, it's fine because what we can do is we can assume a volume. So the easiest thing is assume 1 liter. If you assume 1 liter, then we can calculate the moles, and then we can calculate the pressure. And we can convert all those molarities into pressure by assuming a volume. And it's not going to make any difference if we assume 1 liter or 100 liters, we'll get the same answer. It should be. The other thing that we could do is we can calculate Kc and then convert that into a Kp. And we convert it into a Kp, and then Keq in this case is equal to Kp because it's all gases. And it's not equal to Kc here. And so what we do is we calculate Kc first and then convert Kc into a Kp. Now the equation for the conversion is not hard to derive, but I just give it to you. Now Kp is equal to Kc RT to the delta N of gas. That was the equation that we use for the conversion. So why don't you see if that does it? But this is the big thing in thermodynamics and this is what's hard. What's hard about thermodynamics is you have to keep track of all these things, but when you look at the equation, the equation's right. The equation, I calculate K. K is just the concentration of the products of the reactants. The equation looks right, but it's not because there's so many restrictions. All these things you have to keep track of, and it makes it hard. So the goal of this is, at least at this point, is just to make sure you're using the correct equation under the correct circumstances. So this is why I think it's a good exercise to just go back and take a look at all the equations and then just make a note, when they're valid and under what conditions, and you should be okay. But if this is, if you didn't do the Kp conversion, that could be it. That could be why the answers don't match, because the delta N of the gas is -2. And we're losing 2 moles of gas. And then once we have that, then we know that delta G is equal to minus RT, it's under standard conditions, minus RT ln of K. But the other thing that confuses people is this. This is under standard conditions. When I look at my molarities there, are my molarities under standard conditions? No, they aren't. So will this equation work? That would be the next level. The next level is, the first level is just make sure you have the correct equation. If you have the correct equation, you're using it under the correct circumstances, then you're going to be good. But maybe the next level, and you could have higher and higher, or harder and harder levels, is you might think, okay, after you have enough time, let's say you've done that, I got it, now I want to start thinking about some of these things. When you start thinking about some of these things, the K is obviously, the only time K is under standard conditions is if K under standard conditions is always 1. Because if we're under standard conditions, right? But is K equal, how many times does K equal 1? Have you ever seen that in any of the homework problems? No. And so it's very unusual. When we see K spans many orders of magnitude over a wide range from very, very small to very, very large. And so what are we doing here? Why are we using K when the only K under standard conditions is 1? And so these are the things you start thinking about when you start getting bored or something, when you're thinking, I know that, but you want to start thinking a little bit deeper on things. And so it does pop up. But to do that, you have to, and this is what I recommend, you have to, the more time you have, the more time you have to reflect on this kind of stuff, and the more advanced problems you can do. So if you get the basics down first, just feel like stable with the equations, then you can move on up to trying to think, that doesn't quite make sense. It's like if you take the same walk every day, you take the same walk to school. You take the same walk to school, and eventually, done it so many times, you start to notice little things that you might not have noticed before. And so this is like when I was taking I took at UCLA. It was a fun class. I recommend it. It was like history of French film, and they said, okay, for every film you have to watch it twice. You think, oh, why do I need to watch it twice? Once is enough. But you notice a lot of things that you don't notice before, and so you might think, oh, this repetition is not very useful, but it can be very useful because then you start to notice things you haven't noticed. And so, um, but the first step is to get the equations down. So I recommend.
So for this equation, recommend it non-standard. Yeah, the case is one.
No, the delta G is going to be under standard conditions. The delta G will be under standard conditions. When you see a delta G under standard conditions, it tells you how far off you are. So if you see a delta G under standard conditions is very positive, that means you're really far off from equilibrium. So that means the driving force is going to be, well, actually, anyway, if the delta G is very positive, you're pretty far off from equilibrium. And if the delta G is very negative, you're far off from equilibrium. And so they have this curve. I didn't talk about this curve. It's something called the extent of reaction. So if your delta G is here, the driving force is this way. If your delta G is here, the driving force is this way. And this would be at equilibrium. This is when your delta G is equal to 0 there. And so that's just showing, which, actually, I probably should show this curve. I didn't talk about this curve, but probably should have talked about this curve. Delta G and K. Then we have things called extent of reaction. These, that, and delta G. And so we have this, but I didn't want to get into it really. It's already enough to just be able to use the equations, correctly. But this is good to understand as well. But that's if you have the luxury, give them a little more time. You can do it. And so the delta G is telling us, and so we're going to have this reference where this would be the delta G under standard conditions. So if this is actually your Q. So if we're under standard conditions, we're going to just say Q is equal to 1. If Q is equal to 1, do you have too much product? Do you have too much reactant? Which way is it going to go? And so when we look at delta G standard, that's what we're looking at. How far is Q away from K? Which way we have to go. But this extent of reaction, you're going to get hit with if you continue on thermodynamics. So this book is good, even though I skipped a lot of stuff in this chapter. It's good because this will serve as like a good intro for more advanced thermodynamic class. You might have. All right. So anyway, then we just plug it in there, and we can get our delta G on under standard conditions. Well, K is not going to be 1. The question was, K is not 1. So if K is not 1, how can this be under standard conditions? And so so what I was trying to say is this: if K is not 1, how can this be under standard conditions? It's just a reference point. So if your Q is 1, how far is it away from K? If equal to 1. Let's say you had this unusual equilibrium and K is equal to 1. The product and reactants are 1-to-1 ratio. That's unusual. But let's say that were true. Then your delta G naught is 0 because that means you're right on. If K is 1, then it's perfect. You're at equilibrium, there has to be no change. Well, let's say K is like 10 to the minus 16. If K is 10 to the minus 16, that's going to heavily favor the reactants. It heavily favors reactants. That means that under standard conditions, you're way off. And that means your delta G is going to be very large and positive, meaning you're way off if you're comparing it to standard conditions. Your delta G under standard conditions is going to be way off. It's going to be plus 200. Plus 200 is way off 200 kilojoules, meaning that, and so it's a comparison to standard conditions. So what you have to do is you have to understand non-standard conditions. You have to understand standard conditions, and you have to understand how we think in terms of non-standard. In terms of non-standard, it'd be great just to think only in terms of non-standard, but the way we do it is we take non-standard conditions and compare it to standard conditions. And that's the way we do it. And so this is kind of the same thing. We're comparing standard conditions to non-standard conditions. So how far off is K from 1? And that's going to give us our delta G. And our delta G is going to either be way positive, way negative, or right at 0. Does that make sense?
Yeah.
And so these are the things you want to think about. And this is the reason why so many people fail thermo is because it's confusing. Basically, it's confusing. Even people who, my thermodynamics professor said, even people who are thermodynamicists don't understand thermodynamics. Because, the relationships get more. After this, you get thrown a whole bunch of new set of equations. And a whole bunch of new set of equations. If you don't have the original set of equations down, then it's going to be trouble. And so all you want to do right now is just make sure you use the right equation, figure out what equation to use, and then use the right equation for the given scenario, and you'll be okay. I mean, conceptually, I don't know what conceptual questions I asked on the old exam. We can take a look. There are some conceptual questions here. Like number 6. What do you guys get for number 6?
For A and C, because those are saying standard conditions. Obviously, it's not standard. It's at 2 atmospheres.
But it's a reference point. Under standard conditions is a reference point. Well, okay, the speed limit. This is like, okay, what is the speed limit on Crenshaw? I don't know, 35 or something here, or 45, whatever. 35, let's say, 35. But let's say there's a car going 40, in a 35. And then somebody asks you, what is the speed limit on Crenshaw? Well, you say, oh, there's a car going 40. So does the question make sense still or not? So it's a point of reference. The point of reference is you need some point of reference to keep your bearing. Did a person driving 40 miles an hour on Crenshaw change the speed limit? No. And so if somebody asks you what the speed limit on Crenshaw is, and somebody's driving 40 miles an hour, then what would you say? It's still 35, isn't it? And so this is a point of reference. If this were being done under standard conditions, what would delta G be? And so, yeah, the pressure is 2 atmospheres, but now I realize that this is going to be extra confusing because standard conditions is 1 bar. But let's go back. Let's say standard conditions were 1 atmosphere, because it was 1 atmosphere for some time. So if standard conditions were 1 atmosphere, and we're at 100 degrees C, then we're trying to boil water. H2O in liquid goes to H2O gas. Does it boil spontaneously at 100 degrees C? Yeah, so this is a bit tricky. A is true. This is like saying, does water boil at 100 degrees C at 1 atmosphere? What would you say? Yes, it does. Now, that's a point of reference, but we're not at 1 atmosphere. We're at 2 atmospheres. Does water boil at 100 degrees C at 2 atmospheres? The answer is no, it doesn't. But that doesn't matter because A is still true. It's like asking the speed limit on Crenshaw. So does that make sense?
Yeah, I was just confused because of just like the phrase it said, for this reaction at these given conditions,
Mm-hmm.
and then some answers are at different conditions. I don't know if that meant, if it were at the standard, or am I just supposed to disregard and understand what's going to be?
Disregard it. Is delta G under standard conditions. If you had to put in delta G under standard conditions for this reaction, let's say delta G is equal to delta G naught plus RT ln a Q. What are you going to put in for delta G naught? Delta G naught's 0. You plug in 0 into the equation. So even though we're under non-standard conditions, we have to use delta G under standard conditions as a reference point. Ln a Q. What are you going to plug in for this? You're going to say we can't plug anything in because we're under non-standard conditions? No, and under these conditions, delta G naught is 0. We did the calculation in class for this. I don't know. Although we did it for 1 bar, but essentially we did it, and if we were at 1 amp, it was 99 and a half degrees. So I probably should have put 99 and a half degrees under 1 bar. But this was under, for this test, I think I did it in atmosphere.
I see that true, it wasn't 100 degrees C, it was 120. Would G not be less than 0?
Yep. Yeah. It would be less than 0. It would be, and we could calculate it. So plug in that temperature.
But for this one, it's greater. Just
No, it's actually less than 0 because at 1 bar, water boils at 99 and a half. We're at 100 degrees C,
so it's not.
and so we're actually at a higher temperature, which is going to make it delta G more negative in this particular case.
And then how do you figure that out? That it's not. That's at 99.
How did we figure out it was not 99.5? There are multiple ways. I could have figured it out. Probably the one that requires the least amount of thermodynamics to figure out. Is using the Clausius-Clapeyron equation. Could have used that. Let's show you. Let's see.
What we did in class when we did this one is, we set delta G equal to 0.
Yeah,
And then see what temperature
that's correct. We did it. We did it that way. I'm going back to Chem 1A. If we could have done this just using Chem 1A stuff, that we could have figured it out using Clausius-Clapeyron equation. And the way we could have figured it out using the Clausius-Clapeyron equation, well, take a look at your notes because I already did it that other way that Colin was saying, but I didn't do it this way. So we might as well do it this way just to show you an alternate way you could have done this. Here's why this is not working. Or do you, when I say using the Clausius-Clapeyron equation, does that seem fairly straightforward, or? Okay, finally. Great.
Are you going to do it for this problem or the one that we did in class? Because this problem, it's at 100 degrees C, 2 atmospheres.
Well, I'm going to do it for the one we did in class because the question was, how did we figure out it was 99.5 degrees C? How did I figure out the boiling point was at 98? Was this. You could use this equation or you could do it the way we did in class. Take a look at the way we did in class. But we have to know the normal boiling point of water. What is the normal boiling point of water? Yeah, although this delta H, this is just from class. 100 Celsius in the pressure, 1 atm. In class, I made sure to be consistent with bar. So this 100 degrees Celsius is not for 1 bar. This 100 degrees Celsius is for how much pressure? 1 atmosphere. 1 atmosphere is equivalent to 101,325 bar. So I know that. And so this is my given. So what I need to go is I need to go to 1 bar and figure out what the temperature is. And so I just plug it in. Delta H of vaporization is minus delta H of vaporization is minus 44.0 kilojoules per mole. Yeah. This was given in chapter 7, though, as a given. You didn't, I don't know. No, maybe it wasn't given. Maybe they made you calculate it. I can't remember. And so we solve for T2. Just plug everything in and solve for T2, and then we come up with a T2 with this many Kelvin. We had to change this to Kelvin. And then it came out to 99.5 degrees C. This is another way we could do it, but this Clausius-Clapeyron equation came from another set of equations in thermodynamics, which you could use to figure out the same thing. These are all related equations, so this is what we could do. And so that's how we figured that out. It's 99 points. So this particular problem I should talk about because it's debatable. So somebody could say A is false. A is false because we're under standard conditions, and under standard conditions of 1 bar, water does not boil at 100. Boils at 99.5. We're at a higher temperature, so that's going to make delta G even more spontaneous. So to fix this should say delta G naught is less than 0. Then that would be correct. So this answer, you could argue, is wrong. It's false. Or you could argue it's true if we said that standard is 1 atmosphere. then this would be true. What about this one? This is false because at 2 atmospheres, water does not boil at 100 degrees C. So we're here at delta G. Water's not going to boil at 100 degrees C at 2 atmospheres. How about this one?
Also false.
This one is, this is delta G under standard conditions greater than 0. That would be false. If anything, it's 0 or less than 0. And then this one?
Also false. Because we said it's more spontaneous. That one.
More spontaneous under standard conditions at a higher temperature. But this is under standard conditions or non-standard conditions?
Non-standard.
This is 2 atmospheres is non-standard or standard? And so does water boil spontaneously at 2 atmospheres at 100 degrees C? No. And so this is true. It's true. And so the debatable one is A. But if a situation comes up like this and we're test, then you write little notes. Like if this were a test, I would, I could argue one way or the other. I'd write a little note for the professor, assuming this is false, assuming that this is true. And we can cover our bases that way. But write it on the test itself. So you have it documented, if there's something that's ambiguous like that. So all this stuff to keep track of, again, is just like, repetition, drilling, and that kind of stuff. And then just making notes to yourself, use this, use that. Every problem, what I do is I look at it in the homework and then analyze it. I use this equation because of this, this is what I did. And then that's helpful too. So take a look at that. Were there other questions on chapter 13? Okay, we have to move on because we have the lab today. I want to get through the lab, but I need to talk a little bit more about chapter 16. So again, the Clausius-Clapeyron equation came from thermo in chapter 13. It gives us additional options. Okay, we're back to chapter 16, and our lab deals with chapter 16 stuff today. And so we have something called Ka. It's called acid hydrolysis. Acid hydrolysis is when you take an acid and react it with water, how much does it hydrolyze? If it hydrolyzes close to 100%, then we call it a strong acid. If it hydrolyzes much less, then we call it a weak acid. And we can get the ratio using Ka here. Now, there are 2 types of problems that we're going to encounter. One type of problem is to determine Ka. All the acids, somebody else has already done the work. But let's talk about the 2 types of calcs we're going to do. One is to determine Ka. And the second type of calculation we're going to do is we're going to use Ka to determine the equilibrium concentrations and the percent ionization. Now, the percent ionization is funny. It's not fixed. This varies depending on concentration for the same acid. So it would be nice if the percent ionization is always fixed, but the percent ionization changes. And since it's not a fixed number, we don't say, acetic acid always has this percent ionization? Well, it depends on the initial concentration. All right, to determine Ka, then what we do is we try to fill in the ice table here. And so I just love the ice table, we have the HA initial. And the way we always set up these problems, H2O is a pure liquid. The way we always set up these problems is we assume nothing has hydrolyzed initially. Obviously it's already at equilibrium, your acid with water. When you see that bottle of acid, it's already reached equilibrium. But for us, we are going to set it up assuming that we just added the acid to the water, nothing's happened yet. And then we're going to see how much change. If there's a huge amount of change, we call it a strong acid. If there's a small amount of change, we call it a weak acid. And so we'll get HA initial minus X. We'll have X molar here, X molar here. In other words, HA initial minus X is what we call HA at equilibrium. X is what we call hydronium at equilibrium. And A minus X is the A minus at equilibrium here. All right, so when we're doing one, we can determine Ka. The way we determine Ka is we measure the pH. The pH measures this. And then we know how we mixed it up. How many moles of acid do you add to the water? And so typically this is going to be given. And so determining Ka, we have the initial and we have the hydronium, and then we can figure out the rest of the table to determine this. All right, in order to determine the calculation 2, we use Ka to determine the equilibrium concentration and the percent ionization. And so we have to be given Ka here, and we have to be given the initial concentration here. Okay, then we can determine the rest of the table. And so those are the two calculations we do. Today we're going to measure the pH, and so we're going to do both these calculations here. Let me do something here. A moment. All right, so we'll do these calculations together when we do this, but the first part is just to measure the pH. And we have some equations. So the pH is a power function. The power function is a negative log of the H3O plus concentration, or the H plus concentration. And we can take the anti-log of that. So the H3O plus concentration, this is going to be at equilibrium, is equal to 10 to the minus pH molar. We can figure that out. And so from these we can get that. Okay, so let's go ahead, and what we're going to do is we're going to check out the equipment. Have you guys used the pH meters? Did you use the pH meter in Chem 1A? No? No. You guys did, right? Use the pH meters. So the first step we're going to do is we're going to do the calibration of the pH meter. We have enough pH meters for everyone, but you can work with a partner if you'd like. But we're going to use those. Do you see the red solution and the green solution back there? Those are called buffer solutions, and buffer solutions have a very stable pH. In fact, we're going to talk about how buffers work later. But we have two standard solutions there. There's like a pH 4.01 and a pH 7.00, I think. Now, the pH changes with temperature, so you have to look at the label there. On the label, it tells you what the pH is at a particular temperature. And so we're going to go ahead and calibrate the pH meter, and then we're going to measure some pHs of different solutions, and then we're going to figure out the ice table from that and either calculate Ka or use Ka. Actually, we're going to do both calculations for each acid because the Ka values we can look up in a book. We also have Kb, and so we're going to do the same thing for Kb, except we have to do an extra step here. And so Kb, we're taking a base plus water. This is base hydrolysis. So a strong base is going to hydrolyze completely. A weak base, it partially hydrolyzes. So it depends on how much hydrolysis we have here. But this is our Kb equation. And so we can set up an ice table the same way we did for Ka. This is going to be the A minus initial water we omit from the ice table. Ha we assume is 0. So we have 0 hydrolysis to begin with. And then we go minus X plus X plus X. And so at equilibrium, I'm going to have A minus minus X molar, and X molar. This is going to equal the A minus at equilibrium. This is going to equal the H3O plus at equilibrium, or no, HA at equilibrium. And this is going to equal the OH minus at equilibrium. So when we're dealing with a base, we have to do one extra step. What happens is the pH measures the H plus. At equilibrium. It turns out that the H3O plus and the OH minus are connected with one another. And in pure water and all solutions, there's a seesaw relationship between H3O plus and, which I'll talk about more. Actually, maybe I should talk about it now. There's a seesaw relationship between the hydronium and the hydroxide. That is, the hydronium and the hydroxide, one is 1.0 times 10 to the minus 7, the other is 1.0 times 10 to the minus 7. And so we have 1.0 times 10 to the minus 14. We call this Kw. And so I talked about Kw. Kw is Ka for water and Kb for water. This is the Ka for water and the Kb for water. Water can go either way. And so what happens is this. If the hydronium goes down, the hydroxide goes up. If the hydronium goes up, the hydroxide's got to go down. And so there's the seesaw relationship with this. One goes up, the other must go down. We'll talk about this more later. Today we're just going to do the measurements. And therefore, we have this. If we use the property of logs, so what we can do is we could do negative log of this is equal to the negative log of the Kw, the hydronium times the hydroxide. And so what that comes out to is it comes out to the negative log of the hydronium plus the negative log of the hydroxide is equal to the negative log of Kw. Well, the negative log of x, this is a power function, is equal to the px. Oops, not pH. This is the definition of the power function for us. Px, power function of x, negative power function of that. So this is just the pH plus the POH is equal to the pKw. The pKw is 1.0 times 10 to the negative 14. So it would be the negative log of 1.0 times 10 to the negative 14. Well, the negative power of this is 14, and we're allowed 2 sig figs. So this is equal to 14.00. So we have multiple ways we can deal with this. We need the hydroxide concentration at equilibrium. That's what we want. And so there are 2 ways we can calculate the hydroxide concentration at equilibrium. One, we can get the pH and then just go straight to the POH. So for example, if the pH were 8, then the POH is 6. So it's simple. And then calculate the hydroxide concentration. This would be the quickest. This would be the hydroxide concentration at equilibrium. The long way would be, we calculate the pH, and from the pH we could calculate the hydronium ion concentration at equilibrium. And then from the hydronium concentration at equilibrium, we can calculate the hydroxide concentration at equilibrium. That would be a little bit longer way. You have to do more punching in the calculator to do this. And so by far the easiest way to do this is just to do it the first way. Here. Once we have the hydroxide concentration at equilibrium, then we can calculate Kb here. And so once we get the hydroxide concentration at equilibrium, we can fill in the rest of the table and calculate Kb. Okay. The other calculation that we're going to do is we're going to be given a Kb and then calculate. So given Kb, calculate the equilibrium concentration. And the percent hydrolysis. You know, for strong bases, we're going to have a very high percent hydrolysis, like amide, sulfide, etc. All right, so let's go ahead, and what we're going to do is we're going to check out the pH meters, and then we'll learn about calibrating the pH meters, and then we'll take some measurements. Measurements go by very fast, so we'll spend the rest of the time doing calculations after that.
Did you write this stuff down in the lab notebook?
Yeah, just write it down in your lab notebook. You can do the calculations in your lab notebook as well. So when we have a collection of data like this, there's going to be kind of 2 types of error that we pay attention to. What are those? You know, in laboratory, what types of error are you concerned with? Random error. And so the more data we collect, the more we can minimize random error, because random errors, you know, some values are going to be a little high, some values are going to be a little low. If we can take an infinite number of measurements, we can completely eliminate random error, but we can't. So we just try to take a lot of data. So, you know, run 5, run 6, run 7 would be helpful. But here we have 4. And we minimize that random error by taking the average. But we could be off via the other type of error. What's the other type of error? Systematic error. But I think we shouldn't have systematic error because we calibrated the instrument right before taking our measurements. So usually systematic error is like miscalibration of it. And so systematic error we should eliminate by using a proper lab technique. So now, how accurate are these? All we're going to do is we're going to use a little bit of statistics to give us an idea of how accurate these are. And the accuracy, the first thing we're going to calculate using statistics is something called the standard deviation. I'll just call it STDEV. The standard deviation looks at the spread of these, and it looks at the number of measurements that we do here. And then based on this, it calculates, calculates using statistical analysis how wide this spread should be. And so the standard deviation, we can just have Excel calculate. It's just STDEV. And we have two different types of standard deviation that we look at. Calculates the standard deviation based on the entire population given arguments. We're not going to use that one. We're going to use this one. Estimates standard deviation based on a sample. Because really, to calculate the standard deviation, we should take an infinite number of samples, and then we'll get an accurate standard deviation. But instead, we're going to estimate the standard deviation based on a very small sample size here. And so we're going to use this one, standard deviation S. So just do this, and then just plug in the values we have. And so those are our values to calculate. The standard deviation is also known as like the 67% confidence interval. And so what this means is that that if we were to read this, it's going to be 3.14 was our average. And then we're going to go plus or minus. So let me add that as a symbol over here. Let me close that. Plus or minus 0.04. Actually, let me make sure I'm not rounding that weird. Because this 5, I don't know if it was already rounded up or not. So I'm going to add some more digits here on Excel. Okay, it wasn't rounded. And so that's going to be, I'm going to round it now. I'm going to round it to 0.04. Okay. So what this says is that I have about a 67%, because standard deviation is about 67% of the distribution of measurements here. And we're assuming a normal distribution of measurements, a bell-shaped curve. And so I'm going to have a 67% chance that the true value is within that range. The range is going to be 3.14 plus or minus 0.04. So the pH is going to range from 3.10 to 3.18. And so within the range of 3.10 to 3.18, I'm going to say I have like about a 67% chance that the true pH lies in that range. And so this is called the 67% confidence interval. That's too wide. That means there's like a 33% chance it's outside this range. And so in science, this is too wide. We use about double the standard deviation, about 2 times the standard deviation. But we don't say double the standard deviation. Some people will say about 1.95 or 2 times the standard deviation. Other people will say widen out. And so if we catch 95%, that is, this is going to be the 95% confidence interval, which I'll just call CI for confidence interval. And so I'm going to type in equals, and then I'm just going to go to confidence. And then we have different choices for confidence interval. We're going to do confidence T, returns a confidence interval for population mean using a student's T distribution. Student's T is not for students, it's a mathematician, I think, named student. So we're going to use that. And then we have an alpha. Our alpha is 1 minus our 95% or 0.95 in decimal form, 100 minus, so it'd be 5%. Our alpha is going to be 5% or 0.05 in decimal form. And so that means we have a 5% chance of finding it outside and 95% chance of finding it inside. So that's our alpha. If you want to see what these mean, then you can hit f of x and it'll tell you what they mean. And then the standard deviation we just calculated, that's in cell B11. So I'm just going to click on B11 here. And then the sample size is 4. And that's going to give us a little bit wider means. So if I want the 95% confidence interval, it's going to be 3.14 plus or minus 0.06. That didn't format right, but let me try that one more time. And so this means that the range is going to be 3.08 to 3.20. It's going to be about the range. And so a little bit wider range to get the 95% confidence interval, or confidence limit, whatever you want to call it. So that'll be our CI, the confidence interval. Now the confidence interval changes depending on, these are pretty close, But let's say one were way off. Let's say one person got 2.67. If somebody got 2.67, take a look at what happened to our range now. Our standard deviation went to 0.24, and our 95% confidence interval went to 0.39. Do you see that here? Okay. What happens if we take fewer measurements? If we take fewer measurements, let's say we only took 2 measurements. If I only took 2 measurements, then that should widen. That actually didn't widen. I should have widened it. Because the confidence interval is going to depend on how many measurements you take. So I need to check why this calculation didn't quite work as expected. But it's going to depend on how tight the spread is. That is the precision here and the number of measurements here. And so I need to look at how Excel's calculating this to see what happened there. But anyway, this is typically what we do for these. So let's go ahead and look at our next calculation. Potassium aluminum sulfate is a more difficult case. And so let's look at a little easier case. That is, let's look at acetic acid next. What did you guys get for acetic acid? 2.04. 2 point what? 04? Mitchell, what did you get for acetic acid? 1.88. 1.94. All right, so we're going to calculate our average for this. Which is the most accurate? We don't know because of random error. Could be 1.88, and then the other 3 were off, or it could be 2.04. It's hard to say. So the best thing is we have to use all the data. We can't throw one out, and then we come up with 1.98 as our pH. All right, so for acetic acid, I'm going to use the abbreviation for the acetate ion, which is just AC. And we're going to use H2O liquid. This is different than HA. A is just the generic abbreviation for anion, but AC is specifically for acetate. It's a weak acid, so it partially hydrolyzes water, as do all weak acids, but we want to figure out how much it hydrolyzes water by. And when we set up the ice table, we have the hydronium ion concentration at equilibrium. We know what that is. The hydronium ion concentration at equilibrium is going to equal the negative log. Oh, actually, no. It's going to equal, let me back that up here. we have to take the anti-log, base 10. And so let me do that here. I guess I can't, oh, I can't use the eraser there. So the anti-log is 10 to the minus pH molar. And so this is 10 to the minus, okay, we're going to go with our average 1.98, which is our molar average, or 1.975 if you don't want to round it, molar. Actually, I'm not going to round it. I shouldn't round until the very end, so we'll just add an extra digit, 1.975. Okay, then we just punch that into our calculator. Well, I'm going to have Excel do that here. And so let's go ahead, 1.975. That would be cell E10. E10. So this is going to equal 10 raised to the negative E10. And so it comes out to this molar, 0.1059 molar. So that's what we're going to put in here. Now, the rest of the table is we need to put in the initial concentration of the HAC. H2 is a pure liquid. We leave that like that. And we're going to assume that nothing's happened, 0 molar and 0 molar. So the next thing we're going to do is, what is the initial concentration? So on the bottle, what is the concentration of the acetic acid? 0.1. Okay. So we have 0.1. How many, is it just one or 1 sig fig? What is it? 3 molar? Oh, okay. Okay, let me erase this. Is it 1 sig fig? 3?
Yeah.
All right. 3 molar. All right, so we're going to go to this direction of the arrow. So this is going to be minus x molar, plus x molar, and plus x molar. Now, the hydronium concentration is going to be the same as the acetate, according to the stoichiometry. So the hydronium ion concentration is 0.1059 molar. I'm ignoring sig figs right now. I'm just going to carry extra till the end. The acetate concentration is 0.1059 molar. And the acetic acid concentration here is going to be 3 minus 0.1059 molar, which is going to give us 2.8941. So we have these are our equilibrium concentrations based on the stoichiometry. Now we can calculate Ka for acetic acid. Ka for acetic acid is the hydronium concentration at equilibrium times the acetate concentration at equilibrium divided by the HAC concentration at equilibrium. And so this is going to be 0.1059 squared divided by 2.8941. K's are dimensionless. There are no units, so we'll just punch this in the calculator and see what you guys get. Oh yeah, sorry, 0.01. 0.01. Yeah, that's going to change this. 2.9894. Oh no, actually that's going to be wrong too. Let me redo it. Let's redo it down here. What did you guys get for your K value? You got that? Okay. The accepted value is 1.8 times 10 to the negative fifth. Fine. So let's calculate our percent error. Our percent error is going to be the experimental, which is going to be 3.75, minus the theoretical, or the actual 1.8, divided by the actual 1.8. Since these are all times 10 to the minus 5, I can just factor that out. Actually, and then it cancels. Times 100. What was our percent error for this? Someone have it? You have a 111%. Okay. Is that what you guys got? All right. 1.8. All right. Yeah, over 100% error. So it's kind of a big error, but not that. But you know, that solution only is made to 1 sig fig. If that solution is only made to 1 sig fig, what is the range? You know, if that solution is 3 molar, that can be anywhere from what to what? 2.5 to 3.4 molar. It's a huge range. And so you can't, you know, with a solution only made to 1 sig fig, and I don't like 1 sig fig because the uncertainty is too high. And so, you know, I don't like working with 1 sig fig solutions or 1 sig fig answers or anything 1 sig fig. So anyway, it's a big error, but it could be because we're way off here. So I'm not going to think about it too much. All right, that's calculation 1. The second calculation we're going to do is we're going to be given our K value. And so in this one, we're going to use the K value, Ka is equal to 1.8 times 10 to the minus 5, to calculate the pH. So let's see what it should have come out to, and so the pHs that we should have read. So this is going to be acetic acid hydrolysis. Water is going to produce hydronium and acetate. Here. We say that Ka is 1.8 times 10 to the minus 5. And then this is 3 molar. H2O is a pure liquid. Hydronium 0, acetate 0 at the beginning. And then we're going to go towards the 0. So this is going to be minus X molar plus X plus X. And so at equilibrium, we're going to have 3 minus X, X, and X. Now, we're going to have the hydronium ion concentration at equilibrium at the top, and the acetate ion concentration at equilibrium divided by the HAC. All these are raised to the first power because the coefficients are all 1. And so this is going to be X times X, which is going to give us X squared on the top, divided by 3 minus X on the bottom. We expect the change to be kind of small because of the small k and the large initial. And so let me write here. Because of the small k and large initial of acetic acid, we expect the change to be small. To be small relative to 3 molar. Your book has a ratio, and the ratio is this. You can calculate the ratio if you want. That is, we put the initial concentration divided by K. And if this comes out to, let's say, greater than 1,000, then it could work. You know, the bigger this number comes out to, the better. And so in our case, what does it come out to? This is going to be 3 over 1.8 times 10 to the minus 5. This is for the simplifying assumption. This is going to be like 20,000 or something, right? About 20,000. This is pretty good. And so I don't usually do this calculation. For me, it's so fast to assume the simplifying assumption works and then double check it that I don't bother with this little check here, you know, what the ratio check is. I go straight to it. If I think it might work, I'm going to go ahead and try it. And so this is going to be 1.8 times 10 to the minus 5, which is going to equal x squared over 3 minus x. I'm going to say, using the SA, the simplifying assumption, this is just going to equal x squared over 3, which is going to give me an x equal to what? Okay, thanks. So that means the percent change, which should be less than 5%, is going to equal our x over 3 times 100%, which gives us what for percent change? That is the change over initial. Is that after multiplying by 100? Okay. Which is much less than 5%. And so the SA is okay. We don't have to, the math is not terrible on this one. This is just quadratic. And so it's not terrible. We could do the math. So 0.007348 looks good. So let's go back over here. This is going to be 3 minus 0.07348. Which gives us what? 2.992652. And this is going to be 0.0073448 molar, and this is going to be the same. Okay, let's double check our K value. And this is going to be 0.0073448 squared divided by 2.992652. And what does that come out to? Does it check out? It checks out. 1.8 times 10 to the negative 5 was what it's supposed to be, so it came out. Now, the percent change is given different names here. The percent change is also known as the percent reaction, which is also known as the percent hydrolysis, because this is a hydrolysis reaction. But for acids, hydrolysis and ionization are the same, so this is also equal to the percent ionization. So weak acids partially react. Well, you know, this weak acid at 3 molar only reacted 0.007%. I mean, not, what was it? No, 0.248%, so about a quarter of a percent change. So this is a pretty weak acid. In other words, this is a 0.25%, the ionization here. Reaction, 0.25%. Where strong acids have closer to 100%, you know, ionization. So this is pretty weak. Now, we don't characterize, like strong acids, we say 100% because it's so high. But for weak acids, we don't characterize them by percent because the percent changes. So if I had 1 molar, actually the percent ionization actually increases. So percent ionization is not fixed. Percent ionization varies depending on the concentration. So percent ionization or hydrolysis or reaction versus concentration. And as the initial concentration goes down, the percent ionization goes up for acetic acid. And so the percent ionization varies depending on what we start off with. So the lower the concentration, the greater the percent ionization that we observe. And so it's not a fixed number. All right, finally, let's calculate what the pH should have been. So if I have a concentration of hydronium, then the pH is just equal to the negative log of the equilibrium hydronium concentration. So let's go ahead and plug it in here. So just take the log of 0.0073448. .43. 2.13. Let's take a look at our data here. They're all reading a little bit lower, but it could very well be that our concentration was off, was on the high side. Does that make sense? But in theory, if we made it right on 3 molar, exactly 3 molar, then we would expect a pH of 2.13. That's what they've gotten. So the types of things that we calculate, one, we calculate the equilibrium concentrations by taking a measurement, in this case a pH measurement, and then we could get the equilibrium concentrations to determine the experimental value of K. So it's calculating K from experimental data. That's one. The next type of calculation is we're given the accepted value of K. This K is just an average of a whole bunch of data, experimental data. Come up with that. They don't give us the 95%, but this is based on a huge number of measurements. And then we use the K value here and the initial concentration to calculate the equilibrium concentrations, the percent reaction, and in this case, the pH, which is an added calculation. So why don't you try this calculation? We don't have much time, do we? Yeah, we don't. 3 minutes. For the other acid, do you know what the other acid we have here is? The other acid is ammonium chloride. So let me just write the equation for that. It's not the chloride. Chloride is going to be neutral, essentially, although it's a base. It's going to be the ammonium, which is a weak acid, reacting with water, hydrolyze it. Here we're going to form ammonia, or hydronium. Actually, let's just write it the normal way it's written. Hydronium and ammonia. Okay, so we measure the pH of this one. What did you guys get for the pH? 4.7. 4.7 is 4.70. 4.70 is a weaker base. You know, we're getting closer to 7, pH 7. Or not weaker base, weaker acid. The closer we get to 7, the weaker that is. Well, percentage. How about you, Sam? What did you get for ammonium chloride? 4.04. Mitchell? 4.52. 5.00. All right. So we see some variation here now. This is the precision isn't as good as the last two, but we can see let's go ahead and do the standard deviation and the confidence interval for this. Oops. First thing is I'll get the average, which is 4.565, and then I'll get the standard deviation here, 0.4, and then I'll get the 95% confidence interval, 0.63. So you can see we have a wider spread, and so it's going to be 4.56 or 4.57 plus or minus 0.64. So I'll just write it down here. 4.57 plus or minus 0.64. And so you can see our range is going to be a lot wider. And so we'll take 4.57 minus 0.64. 393. So we're going to be from 393 to 4.57 plus 0.64. 521. So what this says is that we have a 95% confidence that the true pH is going to be between 393 and 521 based on the spread of our data. Okay, so we're going to do the same thing. You're going to calculate the K value, experimental K value, and then you'll calculate the, the theoretical pH that we would have expected, and then see. We can calculate the percent error and the pH is going to be high, but it's all right. All right, so I'm going to stop here. We're out of time, but this is going to be the report. You're just going to do the calculations for these on the report sheet, okay, using your numbers. You can do it in your lab notebook, it's fine. Then you can just make a scan of it, turn that in for your report. All right, that's it. I'll be here in the afternoon from 4:20 to 4:50 for office, and then tonight, 9 to 10. So if you have additional questions, you can ask them. I'll post the key for that last test. Sure.